My scanner's on the fritz and the document camera isn't cooperating, so here we are, COVID-19, day 3 and 4 of Simple Harmonic Motion. Welcome everybody who's tuning in. These practice problems are designed to be pretty comprehensive and the kinds of things you can use to apply simple harmonic motion for. First semester, when we did Hooke's law, we talked about setups of springs in series and springs in parallel. If you take a look at the suspension system on a car, it's very clearly 4 springs in parallel. So those free body diagrams and K equivalents that we did back then stand up in good stead. We remember that springs are the exact reverse of electrical circuits. Parallel is a simple sum of all the equivalent spring constants, and series is that reciprocal formula where it's 1 over the reciprocal of the first plus the reciprocal of the second and all that nonsense. So we're very glad that this spring system is in parallel, although Carolyn was not very glad when she drove over that pothole and was 2 hours late to school and had to keep moving people on by the side of the road because she didn't have a tire iron to threaten skeezes with. Number 2, you've got a vertical free body diagram. You've got a hanging mass with gravity, a very straightforward omega equals k over m. It's just a matter of plugging it in to find the period. Remember that cute little trick. If you're trying to divide by a fraction, just multiply by the reciprocal. This is where the AP sheet gets this formula. It's not coming out of nowhere. They're just showing you a shortcut. Number 3, the free body diagram is a little bit cut off on the side. Sorry about that. Equilibrium means the forces are equal, F on one side and Kx on the other side, so you get a nice little horizontal setup without gravity to muck about with. And once you have that, taking the derivative is no problem. If you could figure out the maximum acceleration without doing any work whatsoever, good, you've learned simple harmonic motion. It's kx over m. Remember, it's just pi radians, or 180 degrees, out of phase with position. When position is to the right, acceleration is to the left. When position is to the left, acceleration is the right. The real chiddush, as they say, the real new material is the idea of doing this in 2 dimensions. And once you've graphed out everything, once you've modeled the motion of a piston engine, as is in just about every car you've ever driven and anything else that works by a piston or a pump, you'll notice that it's simple harmonic motion in the horizontal, simple harmonic motion in the vertical. Put the 2 of them together, look at the phase difference between them. True uniform circular motion in 1 dimension is simple harmonic motion, and we can work all uniform circular motion problems hereafter using this information.